Hello class, welcome to lesson 2.1, 2.5 review. So we're going to be reviewing all the problems from chapter 2 all the way up to this point. So the 5 lessons, lesson 1 all the way to lesson 5. And this is all about segmented bar charts, scatter plots, interpreting scatter plots. We had regression lines, and we had the calculation of the correlation. All right, so question 1. A survey was designed to study how business operations vary according to their size. Companies were classified as small, medium, or large. Questionnaires were sent to 200 randomly selected businesses of each size. Because not all questionnaires were returned, researchers decided to investigate the relationship between the response rate and the size of the business. The data are given in the two-way table. So we have a two-way table with business size in the columns, response to whether they responded or not in the rows. So we want to figure out what is the percentage of those who replied that were large businesses. So it says the percentage of those who replied, which means that they did reply. So that means yes. So out of those that replied, how many were large businesses? So remember, the of goes on the denominator. So of those who replied, so of the yes. So how many total yeses do we have? We have 246 total yeses for that row, right? So that's going to be on our denominator. And then out of those 246, how many were large businesses? Well, it's going to be 40. So you can do 40 divided by 246, and then don't forget to times it by 100 to convert it to a percent. So in this case, let's go ahead and type that in here. Times 100. So 16.2602. It says to round to 2 decimals. So 16.26%. All right, now let's look at one. Yeah, so there's another one that's going to be similar to that later on. We'll get to that. But what happens if they end up changing this of those who replied, if they ended up changing it to percentage of large businesses, for example. If they said the percentage of large businesses that, for example, did not respond, then of large businesses, you would use this as a denominator. And then you would say of those large businesses that were surveyed, how many did not respond? Then you would use 160. Okay, just a little side example there. All right, so the scatter plot displays the relationship between height and field goal percentage for all the basketball players on the 2013 roster of the Brooklyn Nets. So we have field goal percentage on the y-axis, height on the x. So basically they're thinking that the height of the player impacts their field goal percentage. It looks like from the data, the greater the height, the greater the field goal percentage. So they have some kind of advantage. So suppose the equation of the regression line is this guy. Predict the field goal percentage for a player with a height of 81 inches. Type the whole number. So so the height is x, right? So we're gonna plug this in for x and get our field goal percentage. So you type it in like that, and we'll go ahead and we'll calculate this on here. Okay, so we get 47.97. In this case, this is the percentage. So you don't have to type the percentage here. They already have percent on here, but it's going to be 47.97%. All right, the third question. The scatter plot shows the relationship between life expectancy and internet users for 35 countries in North and South America, along with the least squares regression line. So Haiti had a life expectancy of 45 and 8.37 internet users per 100 people. What effect would removing this point have on the regression line? So they're referring to right here, this point. So that's Haiti. Life expectancy, really short, right? 45 years is not a very high life expectancy. But they have 8.37 internet users. If you look at the pattern, usually it seems to be that most of the life expectancies are pretty high on average, right? Around 70, maybe the lowest, aside from the outlier, is like 65. But Haiti has really low life expectancy. So this would be an outlier here. So if we want to remove this outlier, then what's going to happen to the data? Well, right now, you can think of this point as basically a tether this point right here is sort of pulling this line down, right? Because in order to fit the data, the line has to try to get as close to that point as possible without messing up the other points, right? Of course. And so if I were to remove that point entirely, well, then this line has no reason to be shifted downward by that point, right? And so if I were to remove this completely and just ignore it, well, then what happens is then the line goes back to normal, and the line probably is going to look more like this, right? It's going to kind of get more in line with the points. And so what that indicates is that if I remove that outlier, this line will shift up, and so the y-intercept will increase. And the slope, if you notice the slope of this guy, the slope is actually getting smaller. So it's not only shifted up, but the slope actually diminishes. The slope here might be something like this, but then if I were to do the slope this way, it should decrease, okay? Because the reason why it would decrease is because the points here are flatter. If you're trying to fit, like, let's say you're trying to fit points like this, well, then your line may end up looking something like this because it wants to get close to those points, right? To kind of match. So in this case, if you remove the outlier, the slope would decrease. The y-intercept, though, would increase, right? That's what we were saying. The y-intercept, it would go up. So it would be this guy. So slope would decrease, y-intercept would increase. All right, question 4. The large residual indicates that a strong correlation between two quantitative variables. So, okay, so large residual indicates a strong relationship. A strong correlation between two quantitative variables. So that is true. Actually, wait, we're talking about large residual. So remember that a residual is sort of like the error. And so if you have a large error, that means that your prediction is not very good. So if I were to have a bunch of data points here, right, scattered, the data is not very good here, and so my error is going to be large in general, right? My error between my line and my points. And so that means that we have a weaker correlation. So this is actually false. A small residual means that the points are tightly together on a line, and therefore you're going to have a small error. All right, so a survey was designed to study how business operations vary. So this is like the company, the small, medium, or large. But this time I switched to data here. So there are no longer 200 businesses, right? And for all of them, they have different numbers. So we want to complete the two-way table for this scenario. So first off, remember, we're going to be using the clues that we have here to fill in the points. So we have 145, 50, and we have the total. Total is 250. So the total is 250. Well, that means that these numbers here have to add up to 250, right? So then we can figure out what this is. So 145 plus 50 is 195. And then we can subtract that from 250. So here we get 55. So there's 55 medium-sized businesses. That total to 250. And then you want to figure out what this column is by using this total. So we have 145 plus something is 250. So that means we're going to have to subtract. So we get 105. So 105 small businesses actually did not reply here. And then you want to figure out what this is based off of the 250. So 250 plus some number is 700. And if you subtract those, you get 450. So 450 450 that said no, rather, and 105 that said no, that were small. Okay, so then now that we know this total, we can add these numbers together in order to get it equal to 450. So these 1, 2, and 3, those three numbers add up to 450. 105 plus 115 is 220. And then we had to do 450 minus 220, which is 230. And then 50 plus 230 is 280. And then 55 plus 115 is, we got 0, carry the 1. So we got 170. And so if we were to add these three numbers together, we should get 700. And in fact, we do end up getting 700. So this does check out. All right, so now the next question, which of the following statements is not true of the correlation R between the length in inches and the weight in pounds of a sample of brook trout? So not true. And remember, correlation indicates, there's a relationship between those two variables. So, and remember that R has to be between -1 and 1, right? And it could be equal to 1 or 0 or positive 1. So here R must take a value between -1 and 1. So that's true. So therefore, that's not the answer. R is measured in inches. Actually, R is unitless. So that's not true. So that may be the answer, but let's check out the other ones. If longer trout tend to also be heavier, then R is greater than 0. So if R is positive, remember that indicates a positive relationship like this, which means as the weight increases, so let's say from 50 to 100, then in this case, the length increases, right? So they're saying that the length would increase. So yeah, there's a relationship between those two. R would not change if we measured the length of the trouts in centimeters instead of inches. That is also true. It doesn't matter what units you use. It's still going to be unitless regardless. And so therefore, it's B. Biologists assess how closely related similar species are by measuring the number of years since the two species diverged from a common ancestor. Researchers Daniel Bolnick and Thomas Neer compared the years since divergence for 12 different pairs of sunfish species to the hatching success of eggs by a cross between two species. A scatter plot of the results is shown. A hatching success of 100 means the hybrid eggs hatched as often as single egg species hatched. And so, okay, so we have, that's what the numbers here indicate. Hybrid hatching success. A number below 100 means the hybrid eggs hatch less often. Okay, so here we have years since divergence in millions and hybrid hatching in the Y. Okay, so which of the following is closest to the correlation between these two variables? So basically, they just want you to look at the scatter plot and see, well, how strong is that relationship between those two variables? And if you look at this, it looks pretty good here, right? And then it kind of diverges a little bit here. So it kind of moves the line a little bit. So the line would normally be here, but because of those points, you would kind of have to shift it a little bit, right? So it might have to be shifted like this or something. And so those points right there are kind of messing up the strength of this. So this would normally be pretty strong. But with these points here, it just makes it strong, still strong, but not as strong. And so it's definitely not weak though, right? It's still pretty strong. So it's definitely not weak, 0.2. And then remember, this is a negative relationship because it's going down. And so therefore, we're going to choose this one. This still indicates that it's strong. It's just not as strong. All right, residual that is less than 0 indicates an overestimation of the response variable. So if the residual is less than 0, well, that means that it's negative, right? And if the residual is negative, well, then that means that, remember, y equals y, or r residual equals, and this is not supposed to be r, it's supposed to say residual. And so remember that the residual is y minus y hat. And so if the prediction was 1, or if the actual value was 1, but you predicted it to be 3, that would be negative. So that means we would overestimate in this case. So yes, if the residual is less than 0, that indicates an overestimation of the response variable. That's true. Okay, so this is the same example as for the Brooklyn Nets example. I think that was question number 2. So suppose the equation of the regression line is, so they give you the regression line, interpret the slope and the y-intercept. So remember that the equation, the general form of the equation is a plus bx. And so this is your y-intercept. This is your slope. So clearly the slope is from this is 1.27. So the slope of 1.27 indicates that, so let's interpret that slope. That slope over 1, and then remember it's rise over run, right? So it's y over x. So rise over run. The rise is the y, the run is the x. And so we're rising by 1.27 because it's positive for every 1 unit in the x. So this indicates that there is, let's see. So it indicates that there is a 1.27. 1.27 stands for, in this case, the field goal percentage. Okay, so we're talking about percentage here. So there is going to be a 1.27% increase because it's going up because it's positive slope. So there's a 1.27% increase in the field goal percent for every one. In this case, height is in inches. So for every 1 inch increase in the height. Okay, so for every time that the height increases by 1 inch, it seems that the players, the predicted percent increases by 1.27%. And so it seems that there's an edge for every 1 inch that field goal percentage increases by that amount, which is pretty interesting. The predicted field goal percentage, anyways. So for the y-intercept is negative 54.9, and that indicates that. So that means that, well, first off, does that even make sense to have a field goal or to have a y-intercept negative? No, it doesn't make sense to have a negative percentage here for this example. So what this indicates is that for every, well, first off, that number doesn't make sense, but it also means, remember that the y-intercept is when x equals 0. And so if x were equal to 0, that's 0 inches. That means that there's somebody that is alive that is 0 inches tall. That doesn't really make sense. All right, so this definitely does not make sense. It means that the field goal percentage would be negative 54.9 for a player with a height of 0 inches. Nonsensical. All right, next question. There is a positive correlation between the size of a hospital measured by the number of beds and the median number of days that patients remain in the hospital. So they're saying, okay, well, there's a relationship between it and it's positive, meaning that it seems like the greater the size of the hospital, the greater the number of days that patients remain in that hospital. So they found that there was some kind of relationship between those two. Well, does that mean that if I increase the size of the hospital, and in this case, this is not a scatter plot, by the way. So this is actually a segmented bar chart, but you get the idea. But this means that if I increase the size of the hospital, actually this is by the number of beds. So yes, this is actually going to be quantitative. So this will be a scatter plot. So if I increase the number of hospitals, let's say from 5 to 100 beds, is that going to mean that my mean number of sick days is going to increase? Is that going to cause my mean number of sick days to increase? And the answer is no, because correlation does not mean causation. Just because two things are related does not mean that the size of the hospital increased the medium sick time, basically. It doesn't mean that. So it's definitely going to be no. The positive correlation probably arises because for those large hospitals with a large number of beds, people that are seriously ill tend to go to large hospitals. And this is probably why the mean number of days that they remain in the hospital has increased, because of the greater size of the hospital. All right, so there could be other variables at play besides just the relationship that we see here. And therefore, its correlation does not indicate causation in general. All right, so the scatter plot displays, so this is the Brooklyn Nets example again. So it wants you to describe the association. So is it strong? Is it weak? Remember that when you describe a scatter plot, you want to use the DOFS acronym. Okay, that's an easy way for me to remember. Direction, outliers, form, and S is the strength. Okay, so DOFS. Describe the association. So this is the D part of DOFS. So is there a strong, is there a, or direction means positive or negative, or no association. So here there clearly is a positive association. It's going forward, right? So there is a positive association between height and field goal percent. Taller players tend to have a higher field goal percent. This is the F part of Doff's form. Is it linear or is it nonlinear? Well, it doesn't look like it's curved, right? It just looks like it's following in a straight line. It's pretty obvious if it's curved. You'll see all the points maybe go like that, and you can kind of say, oh, okay, well, that's kind of curved based off of the pattern. It's usually pretty obvious if it's curved or not. So in this case, it's obvious that it's linear and not something else, okay? So there seems to be a linear pattern in the scatter plot. The strength, is it strong, weak, or moderate? Well, the points vary somewhat from the line. So we'll go ahead and, like for example, this guy right here, that kind of messes up the relationship. These guys are a little bit far. And so we'll say that because they vary a little bit, they vary somewhat. We'll say that the association is moderate. So outliers, are there any outliers here? So there seems to be one outlier right here. And so we'll go ahead and say that there is one outlier. As long as it varies, this outlier is actually making the relationship more moderate than anything. And so that outlier is definitely something that is pretty far away from the pattern. All right, question 12. So this is a small businesses example, small, medium, large. We want to construct a segmented bar chart to summarize this relationship here. Remember that business size is a categorical variable because we're talking about small, medium, or large. Response, on the other hand, response is also a category, even though they have numbers here. Okay, the numbers have nothing to do with them being categorical or quantitative. It's the variable itself. So is the variable measured? If so, it's going to be a quantitative variable. Does it make sense to do a average for the variable? If so, that's a quantitative. Otherwise, it's categorical. So first off, we said that the size of the business is going to influence whether they respond or not. Okay, so we're thinking that the size of the business explains why they responded or why they did not respond. And therefore, the response variable is whether they responded or not. And the explanatory variable is the business size. So we know that this is X and this is Y. And that's gonna mean that my X-axis has to be business size. So that eliminates automatically this one because the X-axis is response. We don't want that. And this one. So we want the business size on the X, which we have it in those two graphs. Next, we want to have we will have business size down here. And in our key, we want to make sure that we include the two categories, yes or no. So we need yes and we need no. And we want to make our key for that, however way we want to do that. And then the percent goes here. Percent or relative frequency. Either one of those is fine. Relative frequency is a decimal. You could say relative frequency is like a decimal, percent is the actual percent, right? So either one is fine. So you can be at 100% or you can be at 1. 1 means 100%. All right, so notice that these have relative frequencies and not percentages. So 1 would be 100%. For example, 0.9 would be like 90% and so on. So it's fine that it's relative because they're all relative here. And so let's go ahead and calculate. So for a small business, what's the percent for a small business? What's the percent that say yes? So there's small businesses, 200 of them, and 125 say yes, right? So 125 divided by 200. Let's go ahead and do that here. And then times 100, of course. So 62.5%. And let's see if that matches up here. So 62.5% for this is for yes. Yep. So that's about right. So that checks out. And for here, small businesses that say yes, that actually does not check out. Let's see, that's about 30%. So that's not right. And I think the reason being is that they actually included the total. You don't want to include the total in your key, right? In your graph. We don't care about the total in the graph. The total is already indicated by the percent, so there's no need to include that. So therefore, this is your final answer. All right, how strong is the relationship between airfare and distance traveled? The table gives the distance in miles from Philadelphia to 6 cities and the cost of the cheapest flight on a popular discount airline. Calculate the correlation. If you have a decimal, round to 2 decimal places. So you want to calculate the average here for the distance from Philadelphia. You want to calculate the average for the cheapest fare for the airline in dollars. So you want to add these numbers together. So get the totals, divide by 1, 2, 3. You have 5 numbers here. So divide by 5 airlines, or 5 airports. So go ahead and write the number here, X bar, 340 plus 860. We're adding these numbers here, all the way to 1330. Divide that by 5 airports, and we'll get that number in just a second. And for Y bar, add these numbers. All right, so I went ahead and calculated the average. So here the average is 978, but since they wanted to 2 decimal places, 978.00 is what you would have to type into the computer. And then Y bar, I got 148.8, so then make sure to include that extra 0 for 2 decimal places. All right, so we have 978.00, 148.00, or 0.80. All right, so then to calculate the standard deviation, remember the standard deviation is the square root, and then you have to add the distance from x to its average. So the distance from x to the average squared, and then divide by however many you have, take away 1. So we have to take the square root, we have to subtract x with its average. So this is x 340. Subtract that with its average, which we have was 978. Then we got to square it and add, that means add, the next value doing the same thing. So 860 minus the 978, the average that we got for the airport, squared, and so on. Divide that by the total. So we have 5 airports minus 1. Repeat that for SY. So we're going to do the same thing. So this time, instead of X, we'll be using Y here for the airport fare. So the first fare is 131 minus the average fare is 148.80 squared, and so on. Divide that by 5 minus 1. All right, so I went ahead and calculated the here. Now, a good resource to use for this would be to actually use Desmo's online calculator. You can take the square root, and then you could do a fraction, and then type all your numbers there, and so on. So this is the best way to do it, and you can determine, if you're typing in the numbers correctly, because this actually shows all the numbers that you type in. So this is just an example, but Desmo Scientific Calculator is very useful. You could use it for that if you don't have a scientific calculator in front of you. All right, so I went ahead and calculated the standard deviations. Now remember, you want to do the 2 decimals. So this is a 5, so this is going to increase that to a 2. So it's going to be 474.42, and then this one is a 6, so that's going to bump this up. But then because that's a 9, that's also going to bump this up. So we get 26.70. Be very careful when you're rounding this. You're going to get it incorrect if you don't round it correct. If you don't do the correct rounding. So 474.42 26.70. All right, so now we're going to calculate the z's, and now so let me show you the first calculation for z, and then I'll go ahead and just auto-populate the rest of the numbers for you, so we don't have to spend too much time showing you the calculations. And then I'll show you zy and zx, zy. So let's work on those. So let's do the zx first. So zx for the first one, you take x, which is 340, minus its average. Average was 978. Then divided by the standard deviation for x, which is 474.42. And you'll get that number. And then for zy, you'll get, you have to take y minus y bar, so 131, minus its average for y, which was 148.80. Divide that by the standard deviation for y, which we calculated, and it was 26.70. And then you can calculate the zy for that. And then to do the last column, you have to multiply these two numbers together. So multiply zx times zy. All right, so went ahead and calculated the zx and zy. So for the zx, you get negative 1.34, zy is negative 0.67. And you multiply those two numbers together to get about 0.9. Okay, so then you can go ahead and fill those numbers in here, negative 1.34, negative 0.67, and this was actually 0.89 something, but then it rounded to 0.90. And then we can just gotta rinse and repeat for the rest of the values. All right, so went ahead and calculated all the numbers just to save us a little time. And then, so these are the numbers that you get if you were to follow the same process that I showed you earlier. So we have all the numbers here. Once you get all these numbers, you calculate them. Also be aware when you're using the calculator, make sure that you put this numerator in parentheses. If you were to just type this in without doing a parentheses, you're going to get the wrong answer. And I'll show you that here. I'll illustrate that here firsthand. So if I were to do 340 minus 978 on the calculator and then divided it by 474.42, notice that I don't get the answer that I have here. I get a really large number. That's because I didn't put this in parentheses. Now, observe what happens if I put this in parentheses. See, completely different answer. And that's because you want to follow order of operations. You want to do the numerator first, and then you divide by whatever's in the denominator. So that means in order for the calculator to do this, you have to put parentheses in here, because remember PEMDAS. You want parentheses to go first, and then you can go ahead and do the rest of the calculations. So definitely follow PEMDAS and get the calculator to do the same by putting that parentheses around the numerator. All right, so now that we went over that, we're going to add this last column here. We need, remember, the formula for the r involves the zx times zy. We have to add the zx times zy's together. So if we add this column, we get 3.42. All right, and then the formula for r is you add up the last column, which we just did, right? So 3.42. Then you divide by n minus 1, so the number of airports take away 1. So you're doing 3.42 divided by 4. Again, if you were to do this on a calculator, put this 5 minus 1 on a denominator, okay? Don't just do 3.42 divided by 5 minus 1 and expect it to be correct. Put it in parentheses on the calculator, or just use a little mental math and just use 4. 3.42 divided by 4. All right, so if you did that, you're gonna get 0.86 for your r. So that's a pretty strong relationship. That's actually very strong. So it's on the order of really strong. So the next question involves another Brooklyn Nets question or problem. And this time they're saying, suppose a player with a height of 84 inches is observed to have a field goal percentage of 56%. Calculate the residual for this person. Type the whole number. All right, so remember the residual is y minus y hat, the actual minus the predicted. The actual is field goal percentage of 56%, right? So 56. And the predicted, how do we get the predicted? Well, we have the equation, so we can just plug in the height, right? Because x is height in this example. So plug that in for height, and then that'll give us the y hat, which is the field goal percent. So we go ahead and we plug in the x value of 84 here, and then we do the math. Okay, so I get 51.78. And that is a percent. So 51.78%. Oops, yeah, that's the y hat. And so now that we got the y hat, we can go ahead and plug that in here for y hat. So we got 56 minus 51.78. And so it looks like we actually underestimated what the field goal percentage would be. And therefore the residual is going to be positive. And so it turns out it's going to be positive 4.22. Right? And this residual is, in this case, this is a percent, but you don't have to type in percent, just type the number. All right, so survey was designed to study how businesses, operations, so this is the business operations example, but this time they want us to find the percentage of medium-sized businesses. So the of goes on the bottom. So the medium-sized businesses goes on the bottom. Who did not reply? So the medium-sized businesses is on the bottom. How many total businesses? 200 that were medium. And out of those 200 medium-sized businesses, how many did not reply? That's going to be 119. Then we times it by 100. We get our percent. So we have 19 over 200 times 100. So 59.5. All right, again, another business example. Is there an association between the size of the business and whether or not the business replied to the survey? So is there an association? If so, is it weak or strong? And so on. So let's go ahead and look at it. So in order to do this, we had to actually calculate the percentages here. We know that the business size is X. So that means that we're going to calculate it for small, medium, and large. So we know that there are a total of 200 small businesses, and we're going to do it for yes and no. So 200 small businesses, and out of those 200 small businesses, 125 said yes. Same thing for medium. There's 200 on the bottom, but 81 said yes, and 40 said yes for large. We'll calculate those percentages in just a second. For small, 75 said no. 119. This is a 1 right here. And 160 said no. Right, so let's calculate some of those percentages. All right, so we went ahead and calculated the percentages here. And of course, we got to times it by 100 to get the final percentage here. So then what you want to do, you want to observe, is there a difference between those that said yes for small to medium to large? And the answer is yes. It seems like a greater percentage of those that were small businesses actually responded than if they were large businesses. So if they were large businesses, probably the mail got lost in the shuffle or something, or they just didn't care about responding. And so their response rate diminished, right? And so this is the relationship that we see. We see an association, somehow we see an association between the size and the response rate. And so yes, there is an association. So there is an association. So there's an association between business size and response rate, because the distribution of the responses is not the same for each business. So the distribution changes for the size of the business. All right, so in a certain population, there is an approximately linear relationship between the y equals height of females in centimeters and x equals their age in years from 5 to 18. So they're saying that there's a relationship, the linear relationship between the height and the age. So as the age increases, it looks to be that the height increases in a linear fashion. And they give it to you by this equation for the prediction anyways. Which one of the following statements must be true? Okay, so the estimated intercept is 50.3 centimeters. Okay, the y-intercept is 50.3 because remember it's y hat equals a plus bx, and that is your intercept, your y-intercept to be exact, and that's your slope. So yes, that's true so far, 50.3 centimeters. And we can conclude that from the intercept that the typical height of girls in this population is 50.3 centimeters. No, that's not true. Remember that the y-intercept is when x equals 0. So that means that when there's 0 years of age, or in this case, they're saying when there's 0 in age, you know, x is their age. So when there's 0 in age, which doesn't really make sense if you think about it, unless they're just not born, right? So at all, then their height is gonna be 50.3. All right, so that's what that indicates. It's not indicating a typical height at all. So this is not correct. The estimated slope is 6.1, which implies that girls in this population between the ages of 5 and 18 are predicted to grow about 6.1 centimeters in height for each year they grow older. So the slope is 6.1. So we put that over 1. The y is the height. So yeah, they're going to increase by 6.1 centimeters because this is a positive slope, so increase for every 1 year of age, which is exactly what this is saying. It's going to predict it to grow 6.1 centimeters for each year that they grow older. So yes, between ages of 5 and 15. That is correct. Now, one particular 8-year-old girl is 115 centimeters tall. She is shorter than expected for girls her age. If you wanted to verify this, and let's say this was a select all that apply type of question, then okay, so her age is 8, her height is 115. Is she shorter than expected? Well, then you can plug in 8 years old into x here. So you plug in 8 into x, we have 50.3 plus 6.1 times 8. And so the height should be 99.1, yet she's 115. So she's actually taller than expected, not shorter. So this is not correct. A 10-year-old girl in this population is at least 110.3 centimeters tall. Well, if you plug in 10 here instead, then you'll get, so let's go ahead and change this to a 10, 111.3. So it's not 110.3, it's 100, let's see here. All right, so this says it's 110.3. This is 111.3, not 110.3. And plus, it's not at least. So remember, this is saying that a 10-year-old girl is at least 110.3. This is just a prediction. It's not saying that they're going to be that height, right? So there's a lot of things wrong with this statement. It's saying that they are at least 110.3. That's not necessarily true. They can be less than this prediction. They can be greater than this prediction or less than this prediction, right? So that statement is wrong right there. And it's not even 110.3. Okay. All right, so question 18. A school guidance counselor examines the number of extracurricular activities that students do and their GPA. The guidance counselor says the evidence indicates that the correlation between the number of extracurricular activities that are participated in and the GPA is close to 0. A correct interpretation of this statement would be that, so 0 correlation. So if R is 0, what does that mean? That means that there's no relationship at all between the number of extracurricular activities and the GPA. There's no relationship at all. There's no linear relationship, right? Because R has to do with linear relationship. It could just as well be that there's a curve relationship, right? And so R would be pretty close to 0 if it was a curved relationship, because R deals with lines, and that is way far away from that line. And so that makes the R go really down, close to 0. So this means, so active students tend to be students with poor grades. So this is not true at all. So remember, R equals 0. There's no relationship between being active or not and grades. So this is not true. Students with good grades tend to be students who are not involved in many extracurricular activities. Well, we just said that there's no relationship between those. Students involved in many extracurricular activities are just as likely to get good grades as bad grades. The same is true for students involved in few extracurricular activities. While that may be true, that they may just as likely be get good grades as bad grades, I mean, that could possibly be true. That is not a correct interpretation of R, right? R is 0 means that there's no relationship, which means anything could happen. As far as, you know, the linear interpretation. So basically, we don't know what happens. It could be curved or not. We know that it's not linear. Okay, so there's no relationship that is linear. Basically, that's what R states. So we can't really infer any other special circumstances. There is no linear relationship between the number of activities and the GPA. Exactly what we need. If R is 0, there is no linear relationship. It could be curved. It could be that there's no relationship, period. All right, guys, that's going to do it for the video. I hope you took a few things from this or refresh your memory. And as usual, I'll see you in the next one.